Alright, hell yeah. So leave a like if you want me to do this at the beginning of most videos. You know what I mean? Just going over the textbook way to do a problem. We have a firework. It explodes a shard. And we're going to say that the shard that goes horizontal is going to create the lowest angle with the horizon. If it goes straight up and down, that's the steepest angle. Okay, with that said, then we use kinematics. I do the integration approach. Uh, uh, acceleration of gravity in the y is g. So when we integrate and we get our velocity equation, it is just g of t. And then we don't have any initial velocity in the y. Then we integrate again, we get our position equation, and the y is 1/2 gt squared. Cool. In the acceleration in the x direction, there is no acceleration. You know, we don't have an earth over here pulling that thing this way. So we integrate and we get just velocity in the x is just our initial velocity. Cool. Integrate again, we get position is that initial velocity times time. So we get two equations for x and y. Now this is cool. At any given time, it's going to, like at time 1, time 2 seconds, 3, it's going to be on this line. Okay, hell yeah. So what we want to do is just get an equation for this line as like y is equal to something x. You know what I mean? And that's what we do. We solve this for t, and then we get x divided by v naught, and then we shove it into here, and hell yeah, we get that classic equation of a line. Y is equal to 1/2 g. Shove that in, we get x divided by v naught. We got to square it. So then this v naught squares. The 2 goes downstairs, still g. So we get this equation. Once we get this equation, this is the equation for that line, that projectile's line. And the question is just like, hey, what's the slope when it hits the ground? Well, if you want to find the slope at any point, you just take the derivative of that. So hell yeah. So the derivative of this is just dy dx, and it's a simple derivative of x squared. This is a constant, and it can be put outside of the derivation, just like integration as well. So we have 2, and then when we bring down the 2, it cancels with that 2, so we just have g divided by v naught squared times x. Now this is the slope at any point on this that we say in the x direction. If we say x is this point right there, that'll give us the slope at that point. But we don't know that point. We don't know the x at that point. But we do know when x is at this distance over here, this our y value is h. And I should explain that my axis is kind of upside down. Like this is going to be the positive y. I like to do that. Positive y, and this is positive x. So hell yeah. So my g is just a 10 meters per second squared. It's a positive 10 because that's going to cause positive velocity. Hell yeah. So how do we find this x value? Well, we take our two equations, you know what I mean, that we have for x and y. These are the most important ones. These drive the problem. And we say, hey, when this y value is h, so I throw in h for here, I'm going to have h is whoa. Sorry about this. No. This was my y equation. You know what I mean? Sorry to do that one, but hell yeah. So these are the equations that we want, because we still want these kinematic equations where these are my position with respect to time. Like I said, if time is 1 second right there, these equations jive. This same time of 1 second thrown into here creates that of over x down y. You know what I mean? And so those are those points. So when we throw in h into this equation, we're going to get a value for t if we solve for t. And then that's going to be the same time that our x is right there. Hell yeah. So we go h is equal to 1/2 gt squared. And then we have to solve for t. So the 2 goes upstairs, the g goes downstairs, and then, yeah, so that was the one error that I made. Hell yeah, it's cool to make errors. But we have t. So what happens? The 2h goes upstairs. And, oh, yeah, my bad. I redid this. So, yeah, we have to clean up our errors. That's cool. And then the g goes downstairs, and so we have that. So, hell yeah. So this is time is equal to the square root of 2hg. And I had something to cover all this up, but I mean, I guess just to here, we'll see what we do. Damn it. Yeah. So this is, I forgot to catch you on the flip side. Alright, hell yeah, we're back, and now I was supposed to double-sided tape this in. Hell yeah, so the t is 2h divided by g, and then, so now what? So now we throw this into this equation, because like I said, we wanted to find this x value at that time where it hits the ground. If we know it hits the ground in the h direction, the y direction, that's going to be the same time here. So if we find this value of time, you know, it's just letters, but we will throw it into here. So now we'll have v naught square root of 2hg, and now we have our x value. And then we go back to our derivative equation, which is this one, and we can throw that x value in. So let's just do that mentally. We got v naught, cancels one of these, so we're going to have a g divided by v naught downstairs, but then we got to multiply by the square root of 2hg. Okay, and then so, so we get this. So we get g divided by v naught squared, v times the square root of 2hg. Now, in the rest of the video, we go over this into detail, but essentially, we're just going to have a square root of g up top, and then we're going to have a v naught downstairs. So the square root of g will go inside here, so we get 2gh under the square root, and then just divide by v naught. You know what I mean? So hell yeah. And I should have gone over this, is like, you know what I mean, what, so if we have the slope, how does that relate to the angle? You know what I mean? So if this is going to be the slope of that line, that's rise over run, that is going to be this divided by that, you know, this divided by that, so this is dy dx. It's the definition of the derivative, you know what I mean? Because we solve for dy dx at this location. So at this point, this gives us an equation for dy dx, you know what I mean? And just as a value, you know what I mean, dy divided by dx, that's the value that this equation will churn out. And we can see from that the tangent of this angle is the opposite divided by the adjacent. And then so we can say, hey, what's the angle? It's going to be the inverse tangent of dy dx. You know what I mean? And so we have an equation for that. So we could just say the angle is inverse tangent of g divided by v naught squared x. And that'll give us the angle of any point in the x direction. You know what I mean? But we just throw in the special case where our x value is at the ground, and that's this value. And then so for the question, what's the minimum angle of the ground that spark's going to land, is going to be inverse tangent of square root of 2gh divided by v naught. Okay, hell yeah. So that was longer than I thought it was going to take, but now we can just do the rest of the video. So thanks for joining me, and that's a video. Alright, hell yeah. So we have physics for scientists, engineers. This is Sarah Jewett, and we're just going to get to this. You know, we're going to solve this one like it was a test or something, you know, and it's a perfect balance of integration, differentiation, trigonometry. And so what we have is the ground, and then we're shooting up a projectile like a firework straight up into the air, and then it's got sparks going in all directions. And we want to know, when one of the sparks hits the ground, what's the minimum angle, you know what I mean? And so you could say if this explodes at the ground, well, it's going to be totally horizontal, so an angle of 0 degrees. Well, we got two angles, you know what I mean? One is the angle that it hits the ground, you know what I mean? So maybe we'll call this theta. And then maybe the trajectory of the angle that actually explodes, like what's the best way there? And so and I kind of solved it from just a generic angle, but I think it's safe to say you could just intuit that the little fragment that goes out totally horizontally is going to create the lowest angle right here. You know what I mean? Just like a shallower angle when it hits. Because if you have, if you shoot the sparks straight up and straight down, that's the highest angle. That angle is going to be totally 90. And then any angle in between that shoots up, like you have to worry about the horizontal, like because once this shoots up, then it's going to go up for some amount of time and then mirror image and come down. And so it's like you're starting the problem with some sort of downward velocity right there. And I think it's just very intuitive. If you shoot straight down, then you're going to have 90. And in the fragments that are actually just, you know, going downward are going to create a steeper angle. So I think just intuitively you can get to that point where you're just like, hey, it's only the sparks or the fragments that are going with a 0-degree angle to the horizontal right here, you know, that are going to cause this minimal angle. So now the problem is just like, well, how the hell do you find out what this angle is? And so this problem also requires, you know, good knowledge of kinematics. So we're going to say, hey, this is our velocity v naught. And I'm going to use v naught. You know, you could just use v. Commonly, this is just v. But now we're going to say, you have to use your kinematic equations in the y and in the x. So in the y direction, the up and down direction, well, we're gonna do a few things. The first is just gravity. You know what I mean? Hey, gravity is going to be 10 meters per second squared, and so any free falling object, give it 1 second, is going to be have a downward component of their velocity of 10 meters per second. So now for this problem, I better just get to it. We're going to set the coordinates here, 0, 0, and this height is h, but we're going to say, hey, this is the positive, we're going to say, I guess, positive y direction, and then we're going to say this is the positive x direction. So then we can just have gravity as 10. Cool. All right, so now, so our acceleration in the y is 10 meters per second squared. And then so the definition of acceleration is change in velocity, change in time. And if we just write it like dv dt, that's kind of the faster way. Now we can actually say dv dt is equal to 10, and then we can separate variables. So we'll get dv is equal to 10 dt, and then we integrate. We get an equation for velocity. Now this is velocity in the y is equal to 10t plus a constant. You know what I mean? And so if you do the constant out here, when t is equal to 0, what's our velocity in the y? We have no velocity in the y. So cool, it's just going to be 10t. So this problem is kind of classically simple too, because, yeah, we don't have an extra term out here. So now the same thing we're going to do. We're going to say, hey, velocity is change in position, change in time, and then we're just going to write that in. You know what I mean? So you're actually writing this in replace of the velocity. Hey, velocity is change in position, change in time. That's going to equal 10t. We separate variables and we get dx is 10t dt and integrate. You know what I mean? And this isn't going to be the problem to actually explain why this process works. We're just showing the processes involved. And then so you get an equation, and my bad, you know what I mean? Generically, I say change in position, change in time, and we're talking about an x direction. But in our case, our direction is in the y. So for velocity in the y is dy dt. My apologies, we're going to change this to dy dt. And now we have dy dt. And so now we get an equation for y is equal to, now this integrates to t squared, but then we have to divide by 2. So we get and let's just use the generic g, you know what I mean? Because, yeah. So back to here, this is going to be, whoa. So dvy dt is equal to g, and then we'll get our equation for velocity. Velocity in the y is just gt. Cool. And then we'll get our position in the y is, we're going to integrate this, you know what I mean? And so, sorry about that. We're just going to do a G there, a G there, a G there. Yeah, I wanted to do all letters on this one. And so, so when we integrate this, we get 1/2 GT squared. And then if we had an initial velocity, we would integrate that with the t. But we still have a constant, so we still have a plus c. When t is equal to 0, this is just 0. What's our y position? Well, we already said our y position is 0. So hey, this equation jives. So now we have an equation for our y, and hell yeah, we have equation for velocity in the y. Okay, so now we're going to say the acceleration in the x is 0 meters per second because there's no earth over here. The only reason that we have this is there's an earth down here, and in a lot of problems I go over that, Kepler's equation. But yeah, we have no change in velocity in the x. And that is a marvel of physics. The fact that you can throw something that way and it won't change its velocity. You know, minus air drag, but usually air drag is pretty minimal. And that's just phenomenally fascinating. Now, it'll hit the Earth. Yeah, you have to throw it off something real high, but it'll just keep going that way. You know what I mean? It's just super cool. You know, it's not smart to throw objects off high things, but you know, it's just fascinating that yeah, the higher you're standing off something, if you throw something that way, it's just going to keep going that way. Now, the Earth is going to catch up to it, and it's going to catch up to the Earth, but it's amazing. Constant velocity. So that's what this is. So now we have, and this is dvx dt is equal to 0. Separate variables, and we got dvx is equal to 0 dt. And then we integrate. And so we get a velocity of x. We get an equation for velocity of x is equal to just our constant. And what's our velocity x? It's just going to be v naught. Cool. We do the same thing here. And then we say dx dt. Finally, we got the dx dt. That's velocity in the x. That's the definition of velocity in the x. Change in position divided by change in time. Like meters per second. Okay. And so, and that's going to be v naught, and then we separate variables, so we got v naught dt and integrate. And now we get an equation for x, and that's just going to be v naught of t. Okay, sweet, hell yeah. So, I guess we could draw this. But these are the two equations we're interested in, because now, at any given time, 1 second, we know what our position is. And again, this is the positive y, because at 1 second we're going to be over this distance and then down this distance. You know what I mean? And hopefully we'll just take kind of that, like, you know, parabolic arc. Okay, so yeah, so cool, so great. So let's say we're down here. How the hell do we know our angle? Well, this is where it's just like, whoa, we just made an equation for a line. So we know, well, kinda, you know what I mean? So, you know, given any t, I could be like at t0 I'm there, t1 I'm there, t2, t3, and so forth. So we're close to an equation for a line. So this is where it's just like, well, we have two equations. We have an x, y, but 3 variables. You know what I mean? So we could solve this equation for, you know, really anything. You know what I mean? We could narrow these two equations down to at least 2 variables. So that's kind of what we're going to do. Maybe that was kind of confusing, but again, all you're doing is just solving for t over here. So we're going to say t is equal to x divided by v naught, and hell yeah, now we got an equation for t, and we're going to throw that right into there. And now, like, what we're shooting for is an equation for y is equal to x. You know, now we'll have an equation of a line. Equation of a line is like y is equal to something x, and in our case, it'll be an x squared. Okay, hell yeah. This, you know, even though the parabola is downward, we just flipped our axis. You know, instead of this xy, we flipped our axis to be xy. You know, I mean, that's why the downward is positive, and we don't have any negative signs, even though we have an x squared, but it's just kind of a downward. It's because we chose our coordinate system to be that way. Okay, hell yeah. So let's throw this in. So we have y is equal to 1/2 g, and I think we can just do this. This is going to be, so t squared is going to be x divided by v naught squared. So you could write that as x squared divided by v naught squared. You know what I mean? So that's what we're going to have. And so we're going to have x squared divided by v naught squared. Okay, so now we have an equation. And we could maybe just call this g divided by 2 v naught squared, because that's all a constant, and then we get x squared. Okay, so now we have an equation for a line, and there's a lot of things you can do with it. You know what I mean? You could integrate it and find the area under the curve. You know, I don't know what the hell that would give you. It would just give you, you know what I mean? Because okay, so anytime you're doing differentiation and integration, like definitely, so if here's my y, what is this? This is in meters, And then if here's my x, what is this? This is in meters. You know what I mean? So if I integrated, I would get the area under the curve, and that would be just meters times meters. You know what I mean? Meters squared. And maybe that's a useful thing if I actually cared what the area of this shape was. But I'm not into that. You know what I mean? So then, you know, if you differentiate, what is that? So differentiation is the slope. Slope, this is just always a good one. Just rise over run. And I think, like, a lot of people won't write it down. You're like, oh yeah, I've been taught rise over run is slope. But just, hell yeah, write it down. And then you can see that, well, the rise is going to be your y. And so we're going to have y divided by x. Okay. And then so just do the units. So the units on my y equation, because sometimes, hey, you have an equation for a lot of things. You know what I mean? You have an equation for F equals ma, where over here is newtons, and over here is kilograms meters per second squared. You know what I mean? So if you had this as your graph, then if you integrated them, you know what I mean, you would multiply them. I don't know, you know what I mean. So, but anyway, so the slope is just going to be, this unit is going to be meters divided by meters. So we get a dimensionless unit. And I don't even know why I went over that. You know what I mean? Because I don't have a head on me to even explain, like, I don't even think that's useful. Maybe it is, the fact that this is dimensionless and angles are dimensionless. I have no idea, honestly. But what I do know is that what the derivative gives you. So if this is my line, and I take the derivative of this equation, then it tells me the slope at every point. So once I do the derivative, let's do it. So the derivative is real easy, dy dx. And if you're thinking of derivatives, do it like this. Always write the derivative one extra step. Hey, it's dy of x dx. See, hey, this is my equation of x. And then you could even do it one step. You could even say d of g divided by 2 v naught squared x squared. You're taking the derivative of this with respect to x. And then if you're confused about derivatives, don't say the word derivative. Say, hey, when I change x just by a little bit, how does this function change? You know what I mean? But now we have to kind of pick our location. So let's pick, like, right here. Like when I change my x by, like, just 1 meter, you know what I mean? How much does this equation change? So yeah, let's do that. So we're gonna be, hey, this is 10 divided by 2 divided by, let's say our velocity is 10 meters per second. Or I don't know, like, what do you think a projectile? We've done this one before where we think the projectile has a pretty good amount of speed. You know what I mean? Maybe like a bullet. So it's going to be about 120 miles per hour, about 50 meters per second. So yeah, so now we're going to have 50 divided by 50 squared. And now we're just, and now we have our x squared. Cool, so we have this. And oh, sorry. So when 0 stored as x, when we have whoops. Oh, it did not like that. Oh, damn it! I totally lost it. Okay, sorry about that. Okay. So, but when we have so we got 10 divided by 2 divided by 50 squared, and then multiplied by x squared. Okay, so when x is 0, this is 0. Cool, got it. And then let's just throw in 1 meter. You know what I mean? So when we're just 1 meter farther away, so now 1 stored as x, and then we get this. We get 0.002. You know what I mean? So we went from 0 to 0.002, but what did we change our x by? We changed our x by, we went from 0 to 1. So even just right here, you see that, hey, we have 0.002 divided by 1. Let's do that. So divide that by 1. Obviously, it's 0.002, but yeah, that's a very low slope. Like, even visually, like, it isn't right there, like, if we got this picture to scale, isn't that like a slope of 1? You know, like over 1, down 1? You know what I mean? So sweet. You know what I mean? So yeah, for sure. And then so that's going to be the slope at, you know, when x is equal to 0. But then what's the slope, you know what I mean, when x is like 20? Like, well, let's see. Let's get some numbers on this. Projectiles usually stay airborne for about 3 seconds. You know what I mean? Maybe if it's real high, maybe like 3 seconds. So, so we're going to say the x-coordinate after 3 seconds is going to be 50 times 3. It's going to be 150. So now we're going to store 150 stored as x. Right, hell yeah. So this is the only kind of tangent for this problem because we're actually learning derivatives. And I think that's hella important. Else you just do the derivative and get on with life. You know what I mean? But so we're going to say x is 150, and then we're going to throw it into this equation. Perfect. And so we get 45. Now we're going to say x is 151. So we're going to go 151 stored as x. And now we're going to do the equation. So now what our change is 0.602 divided by 1. You know what I mean? 0.602 divided by 1. It's still just 0.602, but now our slope is way more. You know what I mean? So if we carry this problem out hella, well, let's do 10 seconds. Just say we have unlimited height to work with. And so, so now we're going to go 10 times 50. So we're going to be at an x distance of 500. We're going to store that as x. And now let's go back to our equation. And now we're going to go now we're going to go 501 stored as x. And then we're going to store that in. And so now we get a change of 2.002 divided by 1. So even right there, now we're hella steep slope. We're not even at a 45 degree. We passed 45 degree angle territory, and now we have a slope of rise. So we're gonna go over 1, down 2. You know what I mean? So like that's the thing with rise over run is like no one does it that way. If I'm right here, it's like, well, I'm gonna go maybe over 1 mentally and then down 2. But that's like is the same thing as just going down 2 and then over 1. So yeah, your slope would be -2, 1. But anyway, if this is the positive direction, hell yeah, your slope is +2 over 1, and that's what we see. So hell yeah, I think that was a very good. So I do a lot of videos with integration. Differentiation doesn't come up a lot, and I swear it's more confusing because people are just like, it's not the area under the curve, which seems tangible, and then you get the slope, and what the hell is that going to tell you? But in our case, the slope 2 over 1 is going to give us that angle. So let's say at 500, you know, if this thing can get over 500, you know what I mean, and the y value would be pretty high, we would have a down 2 over 1, you know what I mean. So now you could find that angle. If this was 2 and this was 1, now we get into trigonometry world. We need to know, you know what I mean, you could figure out like what the hypotenuse is. Like if all you knew was sine theta is equal to opposite over hypotenuse, and cosine theta is equal to opposite over adjacent, and then Pythagorean's theorem, a squared plus b squared is equal to c squared, you would be fully armed. You don't need to know anything about tangent ever. And that's pretty cool. Like, I just thought of that one because, you know, sometimes tangent's too much for people. But from an engineering world, you need to know, like, hell yeah, we're always dealing with vectors. You know what I mean? We always know the hypotenuse. And then so if this is the angle sun is shining, and this is the sine component. Sine component's always a proportion. It's going to be a number between 0 and 1. It's going to be a proportion of this larger number. Cosine, proportion of this larger hypotenuse. So you need to know sine, cosine, but then you need to know tangent. Just that tangent is going to be the sine side divided by the cosine side. I think that those three, knowing what sine, cosine is, and then what tangent is, that's all you need to know. And then for sure, you know, throw in Pythagorean's theorem anywhere you want to. You know what I mean? But if you didn't know tangent, this is going to be kind of fascinating. So I'm going to say 1 squared plus 2 squared, square root that, it is equal to this side. So 1 squared plus 2 squared is equal to this squared, and then so we just square root. So we go 1 squared plus 2 squared square root of 5. Well, square root of 5 is this side. So now we have that. I'm going to store that as x. So now we have 2.236. And now, how could we, so now that we know our hypotenuse, well, now we could say that sine is equal to 2 divided by 2.236, and then sine of that angle. And then I guess you definitely need to know that, oh, if I'm just trying to find the angle, it's going to be inverse sine of 2 divided by 2.236. So we have inverse, we're in degrees, so we have inverse sine of 2 divided by x, that 2.236, and hell yeah, we get a degree of 63.43. But tangent, just knowing tangent is going to get you there hella faster. You know, it's all right to just know basics that are well-rounded, but if you just, like from the engineering perspective, sine is definitely a percentage of this vector or this hypotenuse. Cosine is a percentage of the hypotenuse, and then tangent is just 2 divided by 1. So, and then I would just know this by heart, is that obviously the angle is the inverse tangent of the opposite divided by, adjacent. You know what I mean? So it's the sine side divided by cosine. So inverse tangent of 2 divided by 1, hell yeah, is that 63 degrees. So that is how we are going to solve the problem. And I might as well just grab a new sheet of paper. Okay, so we didn't solve it fast because we really wanted to work on talking about derivatives. That's probably the most important thing about this problem. And so let's just get this. I think you kind of see what the problem is. So at least, you know what I mean, we are going to rewrite our equations. So we have our equation y is equal to 1/2 gt squared. Our equation x is just v naught t, and then we say that t is equal to x divided by v naught. And then this is going the extra mile. You could just say what t squared is. Sometimes it just visually is just easier to throw in t squared in there, but for most people they're like, what the hell are you doing? You know what I mean? Just throw t in there and then square it, right? So then we're going to get y is equal to 1/2 g x squared v naught squared, and then we'll just rewrite it as y is equal to g divided by 2 v naught squared. So hell yeah, we got our constants to one side. So now we do it. Dy dx is equal to, how do we do the derivative of this? This is going to be the simplest one. So if I take the derivative, see, there's a lot of ways to write this. You know, you could say y is equal to x squared, and then I want to take, or you could just say I'm taking the derivative of x squared dx, or I'm taking the derivative of y of x dx, or I'm taking just dy dx. You know what I mean? So, but you are doing dy, you are taking the change in the whole equation, and you're saying the equation is equal to that thing. So I think that little step gets lost in differential calculus. It is still called calculus. Calculus is differentiating and integrating. Sometimes people just think calculus is the integration part, but that's just me. I have to. That's why I had to say that. So anyway, so and then obviously this is just 2x. You know, that's how you differentiate that. Super simple. So we're just going to bring down the 2. It's going to cancel with that 2, and so we're going to get the change in y, change in x is just going to be g divided by v naught squared x. So the 2 came down, but we already canceled it with that 2. You know what I mean? The 2 would be upstairs, cancels with this 2. Okay, so now we have this differentiation. And so now what we want to do is be like, well, like when this hits the ground, we want to know what the slope is. You know what I mean? The slope will give us rise over run. So dy dx will give us the slope, will give us the rise divided by the run. And let's say it's just 0.5. Well, turn this fraction into something that looks like this, and then we can see that we're going to go down 1 over 2. So maybe we have a shallow slope like that, and this would be 1, 2, down 1 over 2, and down is our positive direction. But then from there you could find the angle. Again, angle is just going to be inverse tangent of 1 divided by 2. End of problem. You know what I mean? So that's what we're going to do. But we don't know, you know what I mean? Maybe we just like, well, we don't know we don't know what x value to put in. So that's why we have the kinematic equations. And the only two you need to use in this problem is the position equations, because at any time, this is going to be your x and y value. These are going to be where the particle is in the x, and then where it is in the y at any time. So at 1 second, it's going to be on that line, 2 seconds, and then so forth. So what we're going to say is like, well, we don't know like how far it's away is going to hit on the ground, but we do know the height. We know it exploded at this height, and so we can say this y side is equal to h. You know what I mean? So hopefully I said that, to where it's just like, no duh. But anyway, so this y side, so we have h is equal to gt squared. So now this is the time that y is equal to h. Sometimes you can put subscripts on this. This helps. Sometimes it hinders. But now the other equation says x is equal to v naught t. And then you can do the same subscripts. Y is equal to h. When these two times are the same, then we are at this height on the ground. We hit the ground, and we're going to be so far over in the x direction. You know what I mean? And then let's just call this d. You know what I mean? So then we're going to say, hey, d is equal to v naught t, y is equal to h. So that's sometimes what I do is just like the generic y, x terms, like sometimes are meaningless because they're just used in a lot of generic ways. So just throwing your own term in, you know what I mean? And then we're just doing that right now for this distance d. Like obviously h, we had to throw in that height. This is the height given in the problem. For our problem, it's just using letters. All right, hell yeah. So we're back, and you know what I mean. So now what do? Well, if we know this h, we can find this time. You know what I mean? So then we can just say, hey, like solve for time. And then when we solve for time with variables of h and g and then some sort of number, then we can throw that in for time, and then we can throw what our distance d is. You know what I mean? Because that's all we're trying to find. We're trying to find those two values. And for our problem, you know what I mean? Hey, we're trying to find d h. See, that doesn't look quite right, actually. You know what I mean? Because you'd want to say, like, hey, x, y. So we're trying to find this x, y position of this line. And then once we know that, we have a derivative that says, hey, if we throw in the x value, then we can get that slope. Okay, yeah. So we don't need both of them. We just know that when h, the time when this equation is equal to h is going to be the same time when this equation is equal to that distance or that x value that we're going to throw into there. You know what I mean? So I really shouldn't have called this d. You know what I mean? And let's not. You know what I mean? Let's just call it x, because this x is what we're throwing into our equation for slope. And then once we get this slope, then we can say, hey, that slope is going to be like 0.5. That's 1 divided by 2. And then so even like right here, you can work backwards. Hey, isn't the angle, the answer that we're going to try to find, isn't that just inverse tangent of the actual slope? You know what I mean? M. So there's just a lot of ways you could write this. Inverse tangent of, well, isn't that just dy dx? You know what I mean? At solved at this distance x. Hell yeah. So there you go. Okay. So yeah. And then even just right now, isn't that just inverse tangent of this equation? G divided by v naught squared x. Like hell yeah. So now, like, once you kind of see the problem, you know what I mean? Like, we're going to do it piecemeal, but you can look a step ahead and be like, oh, okay. And then aren't we just going to throw in that value of x? Sure, but it's going to have other variables. And then so we're going to clean it up just a little bit. But this is where we're headed. All right, hell yeah. So let's solve this for t. So we're going to have 2h. So the 2 went upstairs. I'm going to bring the g downstairs. and then this is equal to t squared. So I'm going to square root it, and then hell yeah, that's going to be equal to t. And and I'm going to get rid of this subscript just because it just kind of makes it bogged down a little bit. So now this is the same time that satisfies this equation for x. And so now we're going to throw it in. So we're going to say x is equal to v naught, and then times this value for t, 2h divided by g. And then hell yeah. So now when we throw it into this equation, we can say, hey, dy dx is equal to g v naught squared. And now times this v naught square root of 2hg. Okay, hell yeah. We got some cleaning up to do. Because anytime you get this square root thing, you can, you can do this. You can say, hey, this is the square root of the top, square root of the bottom. Or you can do this. It's v naught, and you can say, hey, this is 2h to the 1/2 divided by g to the 1/2. And you can do it for each term. This is v naught 2 to the 1/2, h to the 1/2 divided by g to the 1/2. Okay, so if this is, and then start putting terms on the other things outside of the equation. This is v naught squared, cool, but this is g to the 1. So then you're going to have, let's do it up here. So you're going to have g to the 1 divided by v naught squared times v naught is 2 to the 1/2, h to the 1/2 divided by g to the 1/2. And then we can see that g to the 1 divided by g to the 1/2 is just g to the 1/2 on top. And if you wanted to go a further step, you could say, hey, this is g to the negative 1/2. And if that's easier for you, now you can say, well, this is going to be, g 1 minus 1/2, and that's going to be the new term, and it's going to be g to the 1/2. So at the end of the day, we're going to have a g to the 1/2 upstairs. So let's do it. So we're going to have g to the 1/2. One of these v naughts cancel, divided by v naught. And then we're going to have, and I'll just do this, 2h, square root of 2h. But obviously, g to the 1/2 is the same thing as square root of g. So now we're going to have square root of g, square root of 2h. And I swear, doing these steps just a million times, especially explaining, will just increase your math skills. Because you're just like, oh, I didn't know I could just do it 1,000 different ways. So now, obviously, you can just do this, square root of g, 2h. And it's the same principle in reverse. If I have square root of 2gh, because these are products, g times 2 times h, then I can say it's the square root of g, square root of 2, square root of h. Cool. And then divided by v naught. So anyway, so this slope, all said and done, is going to be, 2gh, square root of that, and then just a v naught downstairs. Okay, hell yeah. But we're not done, and I guess I'm just going to grab another sheet of paper. Alright, hell yeah. So this was that slope, not to get confused. So once we know the value for the slope, then we can put it into this tangent equation. You know what I mean? And not to get confused anymore, it's like we already did this. We already did g divided by v naught squared, and then we plugged in this value for x. You know what I mean? So now, like, our equation that we're using is like this one. Hey, we just found the slope. It's just square root of 2gh divided by v naught, and this is the answer. You know what I mean? So we don't even need a sheet of paper. So we just have the angle. And this is going to be the minimum angle because we set it up with the horizontal velocity. The particle that breaks off horizontally, parallel to the surface of the Earth, is the one that's going to make the minimum angle. And when that lands, if it blows up at height h, this is the angle that's going to represent. That angle is going to be inverse tangent of this value of the dy dx. We just solved for dy dx. I think this equation is a little bit confusing now just visually because you have to throw in this value of x right into there. Cool. So our inverse tangent is going to be that slope is going to be the square root of 2gh divided by v naught. You know what I mean? So when I did this problem in 3 hours and then did some generic angle up here, let's call it phi, and then we said, hey, when the change in phi with respect to time is 0, where like, hey, if we're on the horizontal and then we shifted a little bit, did our angle change? Hell no. And then we go just a little bit below vertical, just a teeny bit, did our angle change? Hell no. But then, you know what I mean, if we're at a total 90, you know what I mean, hey, we're going to be a total 90-degree angle. And then if we change our angle just by a little bit, this thing's going hella fast, and it's going to go really high and then really far down. And then look at that, we might have 60 degrees. So just within a small 1 degree angle change, like hell yeah, our with d theta, where the change in this is written wrong. I think we wanted to know what this. So d theta with a small change in d phi. If we're calling this phi, if I change phi just by 1 degree, see that's where I just got confused on even the differentiation, and I can make more videos on that. But if I set this up, I'm saying, hey, I can incrementally, this is phi now, I can incrementally change this angle just by a little bit. And if I'm at 90 and go to 89 degrees, well, hell, maybe my angle down here is 60 degrees. And if I go from at 0 degrees, maybe my angle is 90. So that's a huge change. So what we just found is that, hey, this is the angle that we're interested in, and we call that theta throughout our problem. So yeah, so a small 1 degree increase, 1 degree change in phi from vertical to 89 creates a huge change in our angle. You know, our angle goes from 90 to 60, and heck yeah, we want to know where it's minimum. And the only thing that's you have to keep in mind is that well, now let's talk through this. So, and then once I get to the horizontal, I change my angle just by a little bit. You know, I change my angle from 0 to 1 degree. So we have a change in angle of 1 degree. And then this angle, so I changed d phi, this initial angle, like 1 degree. But the angle down here still keeps that minimum. You know what I mean? It hardly changed. So now we know, but and then that's the thing, going back to like algebra, is like, well, we know that it's either a minimum or a maximum. Either this is the minimum angle or it's like the maximum angle. So that's the only thing you have to kind of double check with your problem, is when you have something like this, when you're saying, hey, when is my change in this angle not changing when I change this angle d phi? Because at that point, when this is equal to 0, and that's how you set it up, then you know either you have a minimum or a maximum, but you just don't know which. So anyway, and I don't know if that's like too much just to even just kind of throw that at the end of this video. Is just like, oh, okay. But I just wanted to share, is just like, well, obviously this problem is real easy if you just assume that the horizontal fragments are causing the minimum angle. And I think you can definitely get there through my example of if they go up, then by the time they get to the horizontal, they're going to have some downward velocity. And this problem cares less about how far it is away from here. It just wants to know the angle that it hits. So it's like you started the problem over with just a downward fragment. And so if a downward fragment causes a shallower angle, that's cool, but it doesn't. A downward fragments cause steep angles, and the best is a horizontal to make sure this angle. And then the problem is still, who cares? Because who the hell cares what angle those fragments make with the ground? It's just a test for your sanity. Okay, so there it was. That wasn't fast. I don't think it was too slow. But sweet. And I don't know if I'm going to put, you know, like do it hella fast at the beginning just so you have a quick rundown of what's going on. But anyway, thanks for joining me, and that's a video.